Welcome back to the discussion of spatial networks. So far we looked at the societal use cases and motivation for learning about spatial networks. For example, all of us use navigation apps on smartphone or on web-based services like Google Maps. We also looked at conceptual models of spatial network. We looked at an entity relationship diagram, but also graph models, which have very nice mathematical and computational properties. So in this video, we are going to start discussion of the logical data model for spatial networks. So at the end of this video, we should be able to describe the need for extensions to the SQL spatial querying language we have learned so far, and also specify specific details such as the recursive querying facility in SQL. So there are different ways to extend and we can list them. All right, so let's again recall the context. We have discussed conceptual data model, and in this case we are in a video we are going to look at logical data model, and we look at two different ways to extend SQL to support queries on spatial networks such as shortest path. And in subsequent videos we will see the details of those two ways, and then we will come back and look at physical data model, how to perform these queries very efficiently on large networks. So first let's look at a basic notion called transitive closure, because this is one way to formally describe the limitations of traditional query languages, including the spatial querying we have learned so far. Okay. So consider a graph G which has a set of vertices V and a set of edges E. Then transitive closure of this graph is described as another graph G star, and it has a set of vertices V star, another set of edges E star. Okay. And formally the set of vertices is same as the set of vertices in original graph. So V and V star are same, but the set of edges is much richer. So not only we have the original edges, but we also add all the paths. To illustrate this, let's look at a very simple graph. So here we have a graph with about 5 nodes, 1, 2, 3, 4, 5. And you also see 5 edges. Okay. So this is your basic graph G. Now if we were to look at its transitive closure, it will have same set of nodes, so 5 nodes, but many more edges, which will represent all possible paths. Okay. So here if you look at G star, so 5 nodes and 9 edges, and here is the picture of that. Okay. So you see the same 5 nodes show up here, but the set of edges is richer. Okay. So where did they come from? They are essentially listing the all possible paths. So for example, notice in the original graph we could go from node 1 to node 4, but there was no direct edge. In order to reach there, you had to either go through 5, 3 and 4 or via 2, 3 and 4. Okay. But nonetheless there is a path from 1 to 4. So in the transitive closure you see an edge from 1 to 4. Okay. So all possible paths have been listed. Okay. So this path 1, 2, 3, 4 for example is listed as 1, 4. You can also see it in a tabular manner. Okay. Now you probably realize that the shortest path query that we are all used to on Google Maps and on your smartphone nav applications are examples of transitive closure. Okay. But in addition to shortest path, there are other transitive closure operations. For example, if you are looking at an electric network, then you might see connectivity. Okay. Will the current flow from point A to B? That's another example of transitive closure. Okay. So why are we talking about all this transitive closure? Okay. The reason is that if you remember the spatial querying we learned so far, it was based on relational algebra, and there is a formal result which basically says that the original SQL and other relational algebra based query languages are not able to compute transitive closure. So in other words, if you wanted to support shortest path using the spatial query language we learned so far with operations like select, project and join, we were out of luck. Okay. Unless we knew the length of the path. If you know your path length is limited to 5 or 10, you could use a sequence of those 5 or 10 joins. But if we don't know the path length a priori, there is no way to do that. Okay. In other words, we need to extend our query languages to support transitive closure. So this discussion happened quite a bit in late 80s and early 90s, and people looked at many different choices, and here are the two basic choices which are possible. So one mechanism to extend query languages is via abstract data type. And this is how we extended basic SQL 3 to support spatial data types like points, line strings, polygons, and we spent a lot of time in previous spatial query language discussion to illustrate that. Okay. Now the same mechanism can be used to support spatial networks. If we can design a set of abstract data types, then we could add it to SQL3. Okay. What may these data types be? We'll come back and see the details in next video, but you can imagine data types like graphs, nodes, vertices, or maybe even paths. What kind of operations we may want on those? Certainly shortest path will be one of them, connectivity and so on. Okay. So if we could design these abstract data types, then SQL3 is capable of incorporating those, and then you will be able to use the existing select statement to query graphs. Okay. However, there is another way to extend query languages, and those are custom statements, and SQL has gone actually that way. So first, the vendors were making their own custom statements. So for example, in Oracle, you will find Oracle SQL, you will find a statement called connect, and this was created for directory acyclic graphs or hierarchies, because many companies have trees, for example, to represent bill of material. What ingredients do I need to produce a particular food product? Okay, and they often want a transitive closure on these hierarchies. So Oracle added this statement, and it's a little bit easier to implement than general graph. Okay, these are not going to help you on shortest path on road networks, because road networks have cycles, right? So a more general approach was taken with SQL3 to add another statement called the with recursive, and that supports general graph and transitive closure such as shortest path on general graphs. Okay. So when we come back in next video, we will look at the details of these statements and then go back and see how to implement them efficiently in the discussion of physical data models. So thank you for your attention. I hope this video showed you the limitations of traditional query languages and motivated you to learn some new features which can support spatial network queries. And look forward to seeing you to discuss the details of these in the next videos. Thank you.